All right, today we're going to tune into the very heartbeat of the universe itself as we dive into the physics of waves and vibrations. So, what do they have in common? I know it sounds like the beginning of a really strange joke, right? But the answer connects some of the most powerful and, honestly, some of the coolest phenomena in our world. Just stick with me and you'll see exactly how they're all linked up. You see, the thing that ties them all together is this idea called periodic motion. It's like this hidden rhythm that's happening all around us, repeating over and over again. You see it in the sway of a skyscraper, and you see it in the light waves that have traveled for billions of years to reach us from distant stars. So what is it really? At its core, periodic motion is just any motion that repeats itself. It's a pattern. Think about a kid on a swing or a bouncing spring. It's that predictable back and forth journey, and it takes the exact same amount of time for every single cycle. This simple idea, this is the bedrock for everything else we're going to talk about. Okay, so from that big idea, let's zoom in a little. We're going to look at the purest, simplest form of this rhythm, which is called simple harmonic motion. You can just call it SHM. Think of it as the single basic building block that once it gets moving creates a wave. All right, let's actually watch this happen. Imagine we've got a simple weight on a spring. It starts right here, stretched out to its maximum displacement. That's just the farthest point it gets from the center. It's been pulled as far as it can possibly go. And right there, at the very peak of its stretch, for just a split second, it stops, dead still. Its speed is zero. At this moment, all of its energy is stored up, just waiting to be released. It's pure potential energy. And then, whoosh, that spring snaps it back. It starts accelerating back towards the middle, and all that stored potential energy gets converted into the energy of motion. That's kinetic energy. It hits its absolute top speed right as it zips through the center, what we call the equilibrium point. Okay, so to really talk about this stuff, you gotta know the lingo. There are three main terms you'll hear. Amplitude is just how far the object swings away from the center. The period, that's the time it takes to do one full round trip. And frequency is how many of those round trips it can cram into a single second. That's it, pretty simple, right? And check this out. This is what I think is so cool. Look at this graph. The blue line is potential energy, and the green is kinetic energy. See how they're perfect mirror images? When one goes up, the other goes down. But that red line on top, the total energy, it stays perfectly flat, totally constant. It's this beautiful constant dance of energy being traded back and forth. Okay, so we've got this little wobble happening in one spot. But what happens if that wobble starts to move? What happens when it travels? Well, that's when it becomes a wave. And this right here is probably the most important thing to get about waves. A wave moves energy, it doesn't move stuff. Think about a ripple in a pond. If there's a leaf floating on the surface, it's just going to bob up and down right where it is. The water itself isn't flowing across the pond, but the energy from the splash definitely is. So how do they do it? Well, waves move energy in two main flavors. In a transverse wave, the particles wiggle up and down, while the wave itself moves forward. Think about shaking a rope. That's a transverse wave. But in a longitudinal wave, the particles push and pull back and forth in the same direction the wave is going. That's how sound works. It's just air getting squeezed together and pulled apart. All right, this is where it gets really fun. What happens when these waves start bumping into things, or even into each other? Well, their behavior gets a lot more complex, and frankly, a lot more interesting. You know, there's one simple rule that governs all of this, and it's called the principle of superposition. It sounds fancy, but all it really means is that waves just add up. Seriously, if the peak of one wave meets the peak of another, you get a bigger peak. If a peak meets a valley, they can cancel each other out. It's just basic addition and subtraction. And from that one simple idea, you get four basic behaviors you see all the time. Reflection is just a wave bouncing off something, like an echo. Transmission is when it passes right through, like light through a window. Refraction is when a wave bends because it changes speed. That's why a straw looks broken in a glass of water. And diffraction is how a wave spreads out around a corner, which is why you can still hear me talking even if you're in the next room. Okay, let's start putting these pieces together now, because when waves reflect and interfere in just the right way, man, you can get some absolutely spectacular results. What you get is something called a standing wave. It's literally what's happening on a guitar string when you play it. A wave zips down the string, it bounces off the end, and then that reflected wave starts interfering with all the new waves coming down behind it. And if you get the frequency just right, which is what we hear as a musical note, they lock into this stable pattern. it looks like it's just standing still, with some points that don't move at all. It's a perfect real-world example of superposition. And that idea, that matching of frequencies, leads us to maybe the most powerful concept we're going to talk about today: resonance. It's what happens when you push something at the exact frequency it already wants to vibrate at. Every little push adds to the last one, building and building the amplitude up to these incredible heights. It's how an opera singer can shatter a wine glass with just their voice. But that power, it's not always a good thing. Resonance can be absolutely destructive. This is exactly what happened in Mexico City back in 1985. The earthquake sent out seismic waves at a certain frequency. And tragically, some buildings had a natural swaying frequency that perfectly matched it. The ground's shaking resonated with them, amplifying the motion more and more, until the buildings literally tore themselves apart, while other buildings right next to them were left standing. It's a terrifying demonstration of physics. So, with all this power, how do we get a handle on it? How do we predict it or even control it? Well, that's where the language of math comes in. Because physics isn't just about watching these things happen. It's about being able to calculate and predict them before they do. Now, don't worry, we're not going to do a pop quiz here. The point of showing you this isn't to solve the problem, it's to show you the power of the physics. Just by knowing two simple things like the mass of an object and how stiff its spring is, these formulas let you predict its entire future. You can calculate its frequency, its speed, its exact position at any moment in time. It's incredible. And really, that's the whole point, isn't it? That's the big idea here. The same simple back and forth motion we saw with the little spring, that same dance of energy, those same rules of superposition, they scale up to explain everything. They explain how an engineer designs a skyscraper to survive an earthquake, and they explain how an astronomer can analyze the light from a galaxy billions of light years away. So it all comes full circle. The earthquake, the guitar solo, the microwave oven, they're all playing by the same set of rules. They're all part of this fundamental, hidden rhythm that's woven into the very fabric of our universe. So now that you're in on the secret, now that you can see this hidden rhythm, what are you going to notice oscillating tomorrow that you never saw before?